All right, well, it's just about the top of the hour, so let's go ahead and get started. Thank you everyone for joining us today. This is our final press conference of Fall Meeting 2020, Wildfire-driven thunderstorms and their role in the climate system. I'm Lauren Lukuma from the AGU Media Relations Office, and I'll be moderating today. So our panelists are Mike Fromm from the U.S. Naval Research Laboratory, David Peterson, also from the Naval Research Lab, and Laura Thapa from the University of California, Los Angeles. Just a few housekeeping notes before we get started. The slides from this presentation will be uploaded to the Fall Meeting Media Center later today and will be available for download as a PDF. This press conference is also being recorded, and the recording will be posted to AGU's YouTube channel under the playlist Fall Meeting 2020 Press Conferences. And after the formal presentation and Q&A portion ends, we will open up a 30-minute informal discussion room via Zoom so that reporters can stick around and chat with the panelists face-to-face or over Zoom for a little bit more discussion and questions. So my colleague Liza Lester will post the link to that discussion room in the chat box of this press conference, and along with the meeting ID and the passcode. And if anyone has any questions or technical difficulties at any time, please email us at news@agu.org and we'll get to you. And with that, I will turn it over to our first panelist. Take it away, David.
All right, thanks, Lauren. So as Lauren mentioned, my name is Dave Peterson. I'm a meteorologist at the Naval Research Laboratory in Monterey, California. If you go next. And so before we get into the specifics of what happened in Australia, we'll start with a little background. And so the focus here is what's called wildfire-driven thunderstorms. And the technical term for this is pyrocumulonimbus, but you'll hear us refer to these as pyro-CB for short. So the diagram there gives you an idea of what we're talking about, but the part I want you to focus most closely on is the updraft mechanism here. So you have a large, intense wildfire, it generates a lot of heat, that hot air rises, and as the smoke plume works its way upward into the atmosphere, sometimes a cloud will start to develop at the top of that. And under certain weather conditions, that cloud can continue developing into a full-size thunderstorm, as you see here. So what ends up happening is you create this chimney-like effect where the smoke being released by the fire is accelerated upward through that thunderstorm cloud, and then it's injected at extremely high altitudes. It's usually at least at the altitude of jet aircraft where they cruising altitudes. So if you show the next image, to give you an idea of what a pilot might see if you were flying downwind of one of these at about 30,000 feet. But sometimes the updrafts are so intense in these pyro-CB, they will actually extend into the next level of the atmosphere above the weather, which is called the stratosphere. And when that happens, you create this similarity to, say, an explosive volcanic eruption. So this is just an example of one pyro-CB. But if we go to the next slide now and we talk about what happened in Australia, we're talking about what we're calling a super outbreak. And this occurred near New Year's of last year. So this was the end of December 2019. So we call this the Australian New Year super outbreak. Reason for that is that in the span of about 45 hours, we had over 30 of these pyro-CB. And that's off the charts. You know, nothing like this has ever been seen. And so if you look at the animation there, you can see what it looked like from space. And so we're looking down. Daytime pyro-CB will show in orange. That's an algorithm we developed at NRL to distinguish pyro-CB clouds. And at night, they'll show in this multicolor display, and you'll be looking for the reds and the yellows. And so here the event starts on the 29th, if you're following. This is at night. And as we work into the 30th of December, you'll see more pyro-CB develop in the orange there, quite a bit along the coast. And then again, through the next nighttime period, there's that big yellow area in the middle that was a big pyro-CB. And then it continues even into New Year's Eve. And so this is a multi-day, extremely large pyro-CB event. To put that in perspective, all previous pyro-CB events have occurred usually within the same evening and featured less than 10 pyro-CB updrafts. So we got more than 3 times the activity here. And if you go next, you know, it wasn't just this super outbreak. There was another phase on January 4th. This particular event was extreme in its own right. I mean, compared to previous events, it still ranks pretty high, but it was kind of overshadowed by this first super outbreak phase. And when you put it all together, if you go next, there were on the order of 38 different updrafts, pyro-CB updrafts, transporting smoke to high altitudes. And the result of that was just 2 enormous smoke plumes in the stratosphere. So if you go to the next slide, I'll give you an example of what happened a couple days after that first super outbreak phase. And you see this giant smoke plume extending across, about half of the South Pacific Ocean. This is thousands of miles. If you look closely, that's the smoke there in the dark color is actually above the clouds. And so this is all stratospheric smoke. And now if we go to the next slide, we get a view of what happened after that second phase of PyroCB activity. So not quite a PyroCB super outbreak, but it still produced a very large smoke plume, again, covering a large portion of the South Pacific downwind of Australia. And then if we go to the next slide, we'll compare this to our previous benchmark for extreme PyroCB activity. So back in August 2017, there was a large event in Western Canada. And at the time, this was considered the unprecedented event, the event that no one had seen before. And it produced a very large smoke plume as well. And if you hit next, this is what actually got us first asking, how do PyroCB events compare to volcanic eruptions? But then if you consider less than 3 years later, we have this event in Australia, and it exceeded this previous unprecedented event on almost every level. So now we're at a whole new level of extreme PyroCB activity. And so if we go to the next slide, we'll put this into sort of a quantitative comparison. This is an updated figure that we had in our previous paper based on that Canadian event. We kind of think of this as a Richter scale for stratospheric impacts. So how much smoke is being injected into the stratosphere by these events. And it's in a log scale, so the events farther to the right are many more times intense than those on the left. And so if you hit next, we'll start at the top here. That red bar represents an intense volcanic eruption a few years back. And the orange bar below that, that's the combined smoke mass injected into the stratosphere by the Australian event. You can see we've very likely exceeded that volcanic eruption. And in fact, if you look at the past 12 years or so, the Australian smoke plume exceeds the majority of all volcanic eruptions in that time span. If you go next, the next bar down, that's that previous benchmark from 2017. And you can see the Australian event is roughly 3 times larger in terms of its stratospheric smoke plume. If you go down again, the events in the middle, those were considered the extreme events prior to 2017. And so now you can see these latest 2 volcanic scale smoke plumes are roughly an order of magnitude larger in terms of their stratospheric impact. And so this is this sort of new class of volcanic scale smoke plumes coming from PyroCB. And if you hit next, the bottom bar there just shows that there's a large range in potential impacts from PyroCB, depending on the event. So if we go next, the question then becomes, where do we go with PyroCB research? These volcanic scale type smoke plumes have kind of adjusted the research questions a bit. And now that we've had this first PyroCB super outbreak, there's questions of, can we expect to see more of those in the future? What does changes in wildfire patterns and that sort of thing in a warming climate mean for the future of these PyroCB events and stratospheric impacts? And then once the smoke is in the stratosphere, what impacts does that have on the atmosphere itself? And so that leads us into our next presentation by Mike Fromm, who will take a look at more of the details once the smoke is in the stratosphere.
Thank you, Dave. I am also a meteorologist at the Naval Research Lab, but I work in the Washington, D.C. area. Next, please. Okay, big picture. This satellite image from a week after phase 1 and phase 2 Australia PyroCBs shows stratospheric smoke in the dark brown shades. This is a NASA instrument in space. And so 1 week after this all started, you had intense smoke, much of it in the stratosphere, all the way from the coast of South America, all the way back to Australia itself, thousands of kilometers long. Next, please. So this was happening this time last year, right around the time the COVID bug was starting to spread around the world. This smoke was starting to spread around the world as well. And we were watching this develop in real time. An international group of scientists attuned to these PyroCB storms were watching satellite data and other data as the Australian spring and summer evolved. And then we saw this super outbreak, and we were all gobsmacked at the things that we were seeing. And in a nutshell, what we have found from this event, post-pyro-CB, that was most interesting, most new, and most important perhaps, was the altitude that the smoke had achieved and the fact that it generated its own circulation in the stratosphere. We'll go into that a little bit more. Next, please. We were all watching this very closely, and to use the analogy to COVID again, we kind of got our own Operation Warp Speed going. Scientists across the globe tried to get the information that they had been discovering out as quickly as possible to inform the science and general community. And this slide shows 3 papers, 2 across the top by Pat Kaplik et al. And Sergei Kaikin et al. Were published this past summer, and one more recently below by Doug Allen et al., another group of us at NRL, published 3 papers on this amazing event. If you look at the titles, you'll see a common thread among the 3, having to do with the altitude of the smoke from the pyro-CBs and this circulation that Doug Allen referred to as smoke with induced rotation and lofting, and he called it swirl for short. Next slide, please. Okay, from the Kaplik et al. And the Allen et al. Paper, we developed this movie of the plume, one of the prime elements of that stratospheric plume from the Australian event that we call a swirl. And this is an animation of meteorological dynamical variables that essentially shows you what the winds were doing in the stratosphere over a 2-month period. And you'll follow the red blob. We'll go through it again. Here it is in, we'll go back, please. Back to January, and in that first week, as it approaches South America, it comes to a halt near South America and then returns back across the Pacific, back over New Zealand, Australia, into the Indian Ocean, southern tip of Africa, the Atlantic Ocean. 2 months later, it was located off the Pacific coast of South America again. And this was all in the stratosphere. These are meteorological dynamics in the stratosphere that were in lockstep with part of this big smoke plume. And that's why it has the name smoke with induced rotation and lofting. So the question is, does this thing really have that spinning character that we have described? And we can do that real quickly and I think easily with some satellite animations. If we go to the next slide, this is a 24-hour animation from GOES visible satellite. Clouds over the Pacific Ocean, you can see the box on the left. And over a 24-hour period, you see cirrus clouds in white and the gray fuzzy clouds primarily in the lower center. If you follow that a couple times, you'll see that in fact, you can see this anticyclonic swirling of that smoke blob. And I've got a little demo for you. You can visualize this with a snow globe. What we have here is a spheroid type plume of smoke in the stratosphere, which is spinning. The smoke is actually creating and also staying trapped in that circulation up in the stratosphere. So what we have is not only do the pyro-CBs, are they weather generated by the fire, but the plume from the pyro-CBs generates its own weather in the stratosphere. And we think we've seen this before. We have studied pyro-CBs for many years now, but with our knives sharpened from having studied this event, we can look back on other events and see that in fact, similar swirling phenomena have occurred that we need to learn a lot more about. So if we go to the next slide, this is a picture, an animation from another GOES satellite back in 2015. Now we're over North America, USA, and Canada. And you see that fuzzy gray long streamer going all the way from Alberta down to the Great Lakes. And up on the northwest side of it, you actually see what looks like a pair of goggles, 2 swirls embedded in that long filament. And these are 2 circulations. And now this plume is actually much closer to where aircraft fly. It's not as high in the stratosphere. But again, it appears that this is telling us that either the smoke is generating its own perturbation in the weather, or the weather caused the smoke to swirl. We need to study that a lot more. Okay, next slide, please. Okay, so what is next? What we have found from this Australian event is quite remarkable, but we also find ourselves in a golden era of satellite data that goes back 20 to 30 years. We have lots of opportunities now with our knives sharpened to look back at other events and compare with what we're seeing now. And we plan on doing that. And we think we have discovered, like I said, certain elements of this super outbreak that have occurred before, but then how much is recurring and how much is brand new. We'll know by observations. But we also need computer models. And I can tell you that we don't have forecast models these days, whether climate or weather models, that involve smoke at this level of detail. These models will need to learn how to incorporate smoke and to test some of these hypotheses that are new and old, having to do with the smoke's impact on weather and climate. And as Dave said, this all traces back to those chimneys of firestorms. So we need to get up close and personal to these pyro-CBs. If we're going to learn its effect, we have to learn the cause. And Laura's going to tell us a lot more about that. Thank you.
Hi, everyone. My name is Laura Thapa, and I'm a second-year PhD student at UCLA. This past summer, I was also an intern at the Naval Research Lab working with Dave. Next slide, please. So today, I'll be continuing the story of pyro-CBs by talking about some observations from inside a wildfire-driven thunderstorm. So next, please. So the big news here is that for the first time ever, scientists gathered detailed measurements from inside an active wildfire-driven thunderstorm in real time. So you've seen the picture on the left before in Dave's presentation, but I'll just reiterate that this was the view from the aircraft when we went and actually sampled one of these pyro-CB storms, and it shows the sun shining through smoke at aircraft cruising altitude. So if you click next, you'll see that we gathered this data using NASA's DC-8 Airborne Science Laboratory, and this was done in the summer of 2019 as part of the FireX field experiment. And I'll talk about this more. So from the outside, this aircraft looks like your normal passenger plane, but on the inside, it's actually a state-of-the-art science lab that can take measurements regarding both the physical and chemical properties of wildfire smoke. And so if you click next, so what we have from the sampling of this pyro-CB are a whole set of brand new science questions that we really weren't able to ask and answer before. But before I dive into those questions, I'd like to give a little bit of background about the Williams-Flats event. So this fire burned throughout most of August of 2019 in Northeast Washington state and was sampled multiple times as part of the FireX field campaign. In particular, we're going to be talking about August 8th, which was the day that this wildfire created a pyro-CB, and it's the pyro-CB that's pictured on the left here. So if you click next. So our first science question was figuring out what was sampled. So what the inset map shows is the location of the fire, as well as the actual path that the DC-8, the research aircraft, used to sample this event. You'll see it's very complicated and that the cloudy environment is quite complex as well. So the first step in any analysis is to figure out sort of what we sampled at what time and at what location. So if you'll click ahead next twice, these are a couple of questions that we can dig into regarding the interaction between the wildfire smoke and the cloud itself, including how does the cloud change the smoke? And then the opposite question, how does the smoke change the cloud? So if you'll click ahead next again, we're also interested in the kind of ecosystems that burn, both in how the ecosystems that burn sort of drive these pyro-CB events, and also if we can observe the signal of the burned ecosystem in the smoke that we sampled. So if you click next one more time, all of these questions sort of tie together in setting us up to infer some downwind impacts of this storm, kind of similar to what Mike was discussing in his talk. So if you click next again, I'll talk a little bit now about sort of the conditions of the fire that led to this pyro-CB. So what happened on August 8th was that the Williams-Flats fire got so big that it split and actually became 3 fires in one. So that's what's highlighted on the left side of this slide. What we're seeing is an infrared image or a heat map, and circled in yellow are the 3 regions of the fire that sort of sprung out of the main fire and drove this pyro-CB activity. So if you'll click next, what we have is a photograph of the full environment that we sampled in. So what happened after the fire split into 3 was that the hot rising air above each of these regions sort of fed these pyro-CB pulses or clouds. So there were 4 total. I'm showing 3 of them here. The first is in its decaying stage. The second is in its mature stage and producing what meteorologists call an anvil cloud. And the third is in its developing stage. So if you'll click next, I'll talk a little bit about how we actually sampled in this environment. So what I'm showing here is a picture that was taken from space using a geostationary satellite. And the fire is in the middle, lower left middle of the image. The blue circle represents a decaying storm cloud that we sampled. So if you'll click next, that shows the aircraft flying through the decaying storm cloud. And if you click next again, you'll see that we also sampled in close in a developing storm cloud. So you go ahead and click next. So now I'll talk about how a pyro-CB acts like a chimney in your house. And this came out of research that I did this past summer as an intern with the Naval Research Lab. So here we have your house, you've got the fire in the fireplace, and what the chimney does is it acts as a pathway that transports smoke vertically from your fireplace to the air above your house. So if we'll let the animation continue, now I've added a thunderstorm on top of this, on top of the chimney in your house. So now imagine this system is like 30,000 feet tall, so many, many times the size of your house. An important feature of the thunderstorm is the updraft, and this is a concentrated region of intense upward motion. And what it does is it pushes the smoke upward, and it acts like a chimney-like pathway that moves smoke from close to the surface to high altitudes. So then the lofted smoke gets released at the top of the storm cloud. And you can think of that as sort of the wisps of smoke that you'll see coming out of your chimney during the wintertime when you're lighting your fire. So if you'll click next, so this is sort of what we expect to see as scientists. We expect to see similar amounts of smoke near the surface as we do at high altitudes. And that's just what this plot is showing, is that the Williams Flats pyro-CB did in fact act like a cloudy chimney. So if you'll click next, I'll switch gears a little bit and I'll talk sort of about how we actually were able to sample this event. So like I mentioned, this pyro-CB was sampled during the FireX AQ field experiment. And I was actually a part of this field campaign as a member of the forecasting room. So I'll talk about sort of like a from the ground to the air type story about how we sampled this event. So what we were doing in the forecasting room is that we were watching the live satellite loops of this event come in. And it was kind of funny because we all had the satellite loops on our computers, and it was also on a big screen in the front of the room. That's what this picture is showing. So we saw the event begin to form in the satellites. And then if you'll click next, you'll see a picture of what we sent to the aircraft. So it was actually really neat. So you'll see the fire is located by the red plus, and far off to the east in Montana is where the aircraft actually was. So it very quickly, like within an hour, made the journey from eastern Montana to northeast Washington to sample this event. And if we'll click next, you'll see what we actually sampled when we got there. So these are photos that Dave took from the cockpit of the aircraft. And you can see the image on the right is the lofted layer of smoke at around 30,000 feet. And the image on the left is a picture from actually flying very close to the active storm cloud. All right, so if you'll click next one more time. So I'd like to wrap this talk up by just thanking the entire FireX AQ science team and leadership. This was a huge collaborative effort, and all the analysis that we've done so far on this data set has also been quite collaborative. So what the photograph shows is the whole team standing in front of the DC-8, and the little photo is me from the day I got to fly on the plane, different day from the pyro-CB, but I got to wear the NASA flight suit, so I thought I'd include that. I'll just wrap up by saying again, emphasizing again how collaborative this effort was. This is a unique data set that fills a gap in our knowledge of pyro-CBs and their interactions with the climate system. And yeah, that's all I have. Feel free to reach out to me on Twitter or by email. I look forward to answering your questions.
All right, thank you so much, panelists. So now we will open it up to questions from reporters who are in attendance. So you can go ahead and write your questions into the Q&A box that's separate from the chat box, and AGU will ask it on your behalf. Please remember to state your full name and affiliation when asking your question. We'll give folks a few minutes to start writing in some questions, but do we have any in the queue so far, Liza?
We do. We already have a few queued up. So we can get started with Rick Levitt, freelancer. He asks, why does the cloud in the stratosphere, the smoke plume, what causes that?
Dave?
Right. So it's very similar to what Laura showed with her chimney animation. And so it all begins at the ground with the wildfire generating smoke that's expelled or lofted through the thunderstorm cloud. And then in these intense cases where the thunderstorm cloud actually penetrates into the stratosphere, that ends up being the altitude of injection, if you will. That's where the smoke is released. And so in the hours and days following the pyro-CB, the cloud will actually sublimate. It'll turn to gas phase. The water vapor will will then become a gas, and you're left with these residual smoke particles. And that's where the story then begins with what Mike showed, with potential impacts on the dynamics and that kind of thing.
Next question is coming from freelancer Catherine Cornai. She asks, what dictates how long a smoke remains in the atmosphere?
Mike, you want to take that one?
Sure. I'd say it's fairly simple, but I think accurate to say that what you need is altitude and amount. The larger the mass of that smoke and the higher it is in the atmosphere, the longer it's going to last. If you put it above the tropopause where our weather occurs, then it's almost guaranteed to last fairly long because there's nothing to rain it out. And if you have a lot of it, then as we've seen, you can actually generate your own weather, which involves lofting of that smoke from, let's say, 15 kilometers altitude up several kilometers higher. And the higher it goes, the farther it goes from falling out. And so it'll last longer. So it's amount and altitude.
And Kathy follows up with a question about, does the smoke pose any danger to aircraft in the way volcanic eruptions do with their ash?
Dave, Laura, you
well,
flew through a smoke plume. What do you determine?
That's right. So in the sense of visibility restrictions and that sort of thing, there is a hazard. And obviously, we're talking about thunderstorm clouds here. And so an aircraft would not want to fly into the middle of that cloud where the updraft can affect the aircraft. Now, in terms of the volcanic influence where you get this impact on aircraft engines and that kind of thing, it's not quite the same thing. The chemistry is different between the volcanic plume versus the pyrocb smoke. But there's still a definite aircraft hazard, especially if you are flying the aircraft near a fire to do the fire suppression activities. So say the aircraft that are trying to drop water on the fire, once something like this occurs, it creates not only a hazardous environment on the ground, but it pretty much precludes any sort of airborne fire suppression.
I'd like to add another element to this, and it's a peculiar thing, but it has to do with lofted smoke. And there was an example of a firestorm in Portugal in the same year of the British Columbia event, 2017. And it was a surprise in terms of how high the smoke got and how concentrated the smoke was. And it was blowing from Portugal over Western Europe, over the UK and France and so on. And what they found out is that aircraft flying through the smoke plume, unaware of what they were flying through, went into an emergency mode because smoke was getting inside the aircraft. And a pilot's worst nightmare is the smell of smoke, as you can understand. So when that happened, and without knowing what was really going on, there were several emergency landings that were called because of that. So in a way, that's a true hazard, but not the kind of health hazard that perhaps you're thinking of, but it's something we need to be mindful of.
And Rick followed up on his first question to say he meant to ask, why does the smoke cloud rotate in the stratosphere? He also asked for Laura, what did you learn from the smoke?
Laura, why don't you go first?
Yeah, sure. So we've learned quite a few things from the smoke so far. These sort of tie in with those science questions that I had on my slides. One of the things that we're quite excited about is learning about the way the smoke particles and light and radiation are sort of interacting with each other, because and how those properties are changing when the smoke goes through one of these storm clouds. So that was a really neat result. And that this result is important because, Mike mentioned in his talk, it really matters to accurately represent these smoke events in models. And if you can understand the way that smoke and radiation are interacting with each other, that's a really important component of models.
Thanks, Laura. And speaking of smoke and radiation, and going back to the other question, this was very new to us. There have been theories about smoke rising in the stratosphere. You may remember the papers that referred to themselves as nuclear winter in that scenario. And that clearly showed computer models showing that smoke would get lofted in the stratosphere. But the details of how it happened were never really known. The models were very, very crude and large scale. What we've observed is the circulations, and what we believe is happening is that the smoke is actually concentrated enough, and it's impacted by solar radiation, and it warms the smoke up. It actually changes the temperature of the air in that snow globe of smoke sufficiently that what happens, and meteorologists probably learned this in school, when you heat the air, you actually can induce a circulation just because the air has to rebalance itself. And that act of rebalancing to spread out that perturbation and heat, it starts to swirl.
And to build on, well, just to build really quick on what Mike and Laura said. So at NRL, we run our own models that include the effect of aerosol particles. And so it's a big deal for us to be able to include these effects that Mike is mentioning in terms of potential impacts on forecast, but also from what Laura's done, being able to get that initial condition right. And so having that direct measurement of the PyroCB helps with that.
Freelancer Megan Sever asks, do you think you're seeing more of these because of more intense fires, or just because we're aware of what we're seeing?
I'll take a stab at that. I think the answer is we still are not sure. But as Dave made quite clear, what we saw in Australia, we are pretty confident we've never seen that before. We can scale up to a whole new realm with what we saw in Australia. But there's still a lot of uncertainty because there have been some very unusual pyro-CB phenomena in the past, and they go back a long time. So it's clear that it's happened, but it's also clear that in my career, there was a time where the term pyro-CB didn't even exist. These plumes were in the stratosphere, but people misattributed those plumes to volcanic eruptions. And it was only by virtue of the discoveries we made at NRL back around 2000 that people started to understand this and to realize that there was a lot going on over our heads that we didn't understand before. And so now we're getting better and better continuously to sharpen our knives, like I said earlier, and get more accurate with observing them and understanding what's happened in the past.
And to add to that, it's understanding how PyroCB may evolve has two different levels. So first there's how much fire is there on the landscape, because that provides the source. And then there's the other piece is, do you have the right weather conditions in place? And so the weather driving PyroCB is a little different from other types of severe weather. It's very dry near and hot near the ground, and your moisture source is actually above the ground quite a ways, say 3 or 5 kilometers up. So we've learned a lot over the past few years and what conditions drive PyroCB development. There is some predictability there, but understanding how this evolves, decade or two down the line, you have to consider both the weather and the fire. And so, there's a couple of pieces at play, and there's a lot of research to be done there yet.
Chelsea Harvey from E&E News asks, could you summarize the characteristics of a fire that are likely to lead to a pyro-CB? Is it the sheer size of the fire, or how hot it gets, characteristics of the fuel, etc., the local weather conditions? Is it easy to predict these events?
I'll defer to Dave and Laura.
Okay, well, I'll start that off by saying, so we had our first sort of operational forecast of a PyroCB during FireX. Laura walked you through that whole process. And based on the work we've done at NRL over the past few years, we knew what sort of conditions to look for PyroCB. We know what type of weather pattern is likely to result in this, and that sort of thing. And so we knew about 3 days out which day that fire was likely to produce one if it was going to. And that helped us plan the flight planning efforts. But these specifics, in terms of especially the type of fire characteristics that are required, are still very much unknown, aside from having a large and hot fire. So the data set collected in FireX will be super helpful for that, because we have really fine scale observations from flying over that fire now, as Laura showed, of what parts of the fire were contributing, and we can dig a lot out of what types of characteristics for the first time. And then, working your way up into the atmosphere, we know that you need a moisture source aloft. These are high-based thunderstorms. The cloud bases are 4 or 5 kilometers in altitude sometimes. And so we know the weather leading to that. So I think combining what we've done in the past with looking at the weather conditions and what we have from these new observations, we can say a lot more going forward and have a lot better handle on being able to predict PyroCB in the future.
Laura, did you have anything you wanted to add?
No, Dave pretty much said it all. I'm just going to emphasize the importance of the FireXAQ data set for this question.
Yeah, that's a really good point. I'll say something that I think can help add some perspective to this. In the case of the Black Saturday Australia event, one of our early benchmarks for a major PyroCB event, that occurred in February of 2009. On the day that the half-dozen PyroCBs blew up, none of those fires were even in existence before lunchtime. So on that summer afternoon near Melbourne, there were no fires, but it was very windy and very hot. So windy that the winds blew over some power lines, electrical towers, and started the fire. And it went from spark to a PyroCB in about 3 hours. And what that means is in that 3 hours, you went from a tiny little fire, which could never produce a PyroCB, to something that was 50 kilometers long in its fire front, and all of it was burning very actively. So you add the area of the fire and the fact that it's hot flaming into what we call instantaneous energy release. And when that gets to a number, and we still need to know what that number is, or what that threshold might be, but when you add it all up, then you can get to the point where the atmosphere overhead can be impacted in a way like a PyroCB.
Henry Fountain from the New York Times asks, how much do we know about any potential cooling effects that these clouds similar to a large volcanic eruption?
I think we know almost nothing. I'm sure that there are works in place right now. There are computer models being run to simulate these recent plumes. And I don't know what all science questions they're trying to answer, but that's, I think, what we need actually is some modeling results to see what that might be. We've looked a little bit at it and determined that we think we can see a signal in cooling at the surface from a PyroCB event. That work wasn't published, and it's still very uncertain. It's a hard nut to crack, but you could expect it to occur. In fact, again, referring to the nuclear winter papers, there were a number of papers that were studying its possible impact, and there are published results showing from real smoke plumes, not PyroCB plumes, but very thick, large-scale plumes, and how they do affect the temperature on the Earth. And it was considerable. So we do have works out there that show that a generic thick smoke plume does cool the Earth. And so we know that it has happened, but we haven't yet done that work for PyroCB plumes, to my knowledge.
Yeah, and to add to that, the PyroCB community is much newer and younger than the volcanic community. So volcanic plumes have been studied extensively. With PyroCB, we're just getting to the point where we can initialize these events in the models themselves. That's why it's so important to have these direct measurements. And it's also important to note that there's no operational weather model that includes the PyroCB effect. And so knowing something about the weather driving them and also about what type of smoke characteristics are in that ensuing plume are very important to being able to answer this specific question and really understand the role that these play in the climate system.
Craig Miller from KQED in San Francisco asks, were there measurable effects from any of these events on California's weather or other? Were actual thunderstorms induced anywhere, or what can we say about actual observed impacts so far? And if so, did these storms produce cloud-to-ground lightning?
I'll defer
So,
to Jim and Laura on that.
okay, well, I guess, Laura, would you want to talk about the PyroCB itself, and then I can talk about California specifically?
Like the Williams-Flats pyrocb?
Yeah. So maybe about the microphysics component.
Yes. See if I can get this on top of my head. Right. So what we have actually in the FireXAQ data set, there's data regarding the cloud microphysics. So that means the size and amount and shapes of the ice particles and water droplets present in a cloud such as this. And Dave can correct me if I'm wrong, but I think the previous theory of pyrocb were they contained like many smaller ice particles, but what we were observing in the Williams-Flats case were a little bit more of the larger ones, which can have different impacts on the precipitation that comes from these storms. I'm not an expert on the lightning formation in a storm like this, so I'll defer to Dave.
Right, and it's those observations that will help us determine the potential impact on lightning. So we do know that PyroCB storms produce lightning. There have even been cases where the lightning will ignite other fires nearby. But you really need these measurements within the cloud to say, a little bit more about how that might happen. Now, the specific question of California. So, 2020 was a very active fire season. And there were PyroCB events observed many times from July through even the end of September, and even October if you go to Colorado. It was a very active year. But it was not at the level of what we saw in Australia or Canada in 2017. But it's still a very active year. There were still a lot of fires and quite a few large PyroCB events in the Western US.
James Stacy Freelance asks, are these events big enough to have an impact on radiative forcing?
So that is one of the big science questions that is currently being examined. There are some preliminary studies that look at this from the 2017 event in the Pacific Northwest of Canada. And like Mike mentioned, I'm sure there are studies underway right now to examine that effect for Australia. But part of that relies on the ability to initialize the plume in the model. And so, first you need to know a bit about the event before you can actually do that type of study. And we, as you see, we have a lot of observations we can leverage there. But that remains one of the large unanswered questions in the PyroCB field.
Carolyn Gramling from Science News asks, can you elaborate a bit on how the smoke might actually create its own weather? Also, how can scientists determine whether the smoke is doing this?
The smoke can generate its own weather in a number of ways. One of the unknowns in the climate science and debate is what we call indirect aerosol effects. And that means that what are aerosols doing to change cloud properties? And what we have learned from PyroCBs, and actually a paper was written on this, is that the smoke that is infused in the PyroCB itself measurably enhances the cloud's lifetime. And what we found is a number of PyroCB anvils that you could actually track with satellites lasting 12 hours, 13 hours longer than we saw from neighboring regular thunderstorm anvils. So that's the indirect effect. The aerosols are actually increasing the lifetime of clouds. And so for as long as those clouds are out there and as big as they are, then they would have an effect of shielding the Earth from sun's radiation and perhaps warming the air at its own level. So you have both of those things going on, aided by this aerosol indirect effect. Even without clouds, as we showed in these images in my presentation, if the smoke is thick enough and large enough in area, then it can actually generate its own weather, its own circulation, and whether that has any teleconnections with events down near the Earth or other weather that we might experience, that is to be determined. But when I showed those two swirling vortices in that jet stream level smoke plume 5 years ago, what that suggests is that smoke can actually change or help to alter the weather in that area of the jet stream where we have what they call the steering currents. The steering currents help us determine what weather is going to develop and where it's going to develop. And so if that steering current is actually perturbed by smoke, then that could actually change the weather not only locally, but even downstream as long as that effect lasts.
Chelsea Harvey from ENEA News follows up on a previous question. Based on what we know about how these events form, do we expect them to change in frequency or severity with continued climate change and the likelihood of bigger and more frequent fires?
My stock answer to that question is that what we know, as was laid out here today, is that what you need for a pyro-CB is for the weather to be hot, dry, and windy. The hotter, drier, and windier it is, the better your chances for these, and you could expect a higher frequency of pyro-CBs. If our climate changes for any area such that it is hotter, drier, and windier, we can expect more. So I think that's a pretty safe bet that if that is something that's predicted to happen and predicted with high confidence, we could expect more of these storms.
But to go along with that, we also have to have at least some conditions in place for thunderstorms to develop over those fires. So there is the situation of these Santa Ana type fires in California, for instance, and that meteorological environment will support a very large fire and rapid spread, but it's not conducive to the vertical development of a thunderstorm cloud. And so there are some other components of weather that go in with this, but obviously putting more fires on the landscape, hotter, drier, and windy, that gives you the first step needed.
Yeah, but I'll also come back. Dave and I have talked about these pyro-CB events. We're amazed at them. And there are some anomalies that actually go to that particular point that Dave just made. And it's something that I still wonder about. There was a fire in San Diego back in 2003 called the Cedar Fire. At the time, it was California's largest wildfire and kept that status for a number of years. And this is in late October of 2003. The Cedar Fire blew up into a very brief pyro-CB. And like I said, I marveled at that because I never would have thought that in Southern California, you could have a pyro-CB, especially in October. So it has happened, and I'm wondering how the weather conditions were there and if we can study that. In Los Angeles back in 2009, the station fire produced pyro-CBs on 3 or 4 days. These are in the hills not too far from Pasadena. And so there were 3 or 4 pyro-CBs that jumped off of the station fire. So again, it's not the type of fire weather that's typically supportive of these, but then things do change. And if they change in the direction of where you have forests and fuels and the weather ingredients all get worse, we can expect more of these storms.
All right, one more question before we head to the discussion room. This is a double header question from Rick Levitt. 1, did these spread fires by lightning strikes? I was caught in one once backpacking and it was spitting lightning everywhere. And 2, what is the cumulative effect of many of these?
So the lightning question, yes. Pyro-CB do produce lightning. In fact, the one that was sampled in FireX had lightning activity with it, which made the pilots kind of adjust their sampling pattern a bit. And I know there's at least 1 or 2 cases out there where the lightning has generated its own fire, a separate fire just from that component. But the cumulative effect, your best example of that is Australia. 38 different Pyro-CB storms, and you've seen the cumulative effect is it's a smoke plume that encircled an entire hemisphere. It had these components that created the rotation and lofting that Mike talked about. And as we speak, that smoke plume is still in the stratosphere, so we're almost a year later. And so it will very likely be the longest lived smoke plume in the stratosphere that we know of. So, you put a lot of Pyro-CB activity together under the right weather conditions, and it can really, build upon itself in terms of creating these really large smoke plumes.
And I'll also add Dave and perhaps Laura are also working on a Pyro-CB climatology. And these big events are pretty much at the edge of the frequency scale of Pyro-CBs, but when you reel it back to the more mundane Pyro-CBs, their frequency increases. So over the course of a summer, for the last 20 years or so, we've been following these. We can count the number of Pyro-CBs globally in the 5 to 6 dozen number. So they are happening pretty much throughout a season at some low level. And that accumulated effect is something that, like I said, the folks on the West Coast at Monterey at NRL are looking at. And I'm very curious to know if they can figure that out, if just the routine Pyro-CBs are altering weather and climate.
Yeah, that's a good point. We get these giant events that we know produce these big impacts, but if we have a season that has a lot of the more mundane, typical Pyro-CB that still reach the stratosphere, what does that mean? That's that question.
Okay, well, that is the end of our open questions. So we will conclude right there. Thank you again to our panelists and to everyone who attended. So now we will move over to that informal discussion room over Zoom, if anyone would like to join us and have a little more time to chat with the panelists virtually. So thank you, everyone. And the link to the discussion room is in the chat box. So you can go ahead and click that. And the passcode is AGU Press, all lowercase, one word. Thanks again, and we'll see you next week. So next week, we won't have any formal press conferences or briefings, but we will have a series of roundtables, which are more informal discussions with researchers on ongoing areas of research. So be sure to check the schedule of those if you'd like to attend. And thanks. We'll see you then. Have a good weekend.